B of this question. The part B of the question is asking, I did the part A in my previous video, so if you want to see that, you can watch these things. And in the part B, the question is asking, compare these values to those of the cascode circuit in figure 8P8.70C, which operating at the same bias current and has the same minimum voltage requirement at the drain as the circuit of figure P8.70 70B. Okay, so here we are just comparing A and C. In the part A, we compared A and B. We looked at the relation between V over tri, we looked at the relation between transconductance, and also we looked at the relation between V over Vi. That's nothing but gain. Okay, so we are going to do the same thing. We are going to compare the V over tri, GM, and the gain with A and C. Let's do that. So I go to create a new page. We are doing the part B. The part B. First, if you want to look at V over tri, in order to see the relation between V over tri and the current, you have to just look at the width over length ratio. If the width over length ratio is equal and the same current, it means the V over tri is same. So we can say V over tri 1 is equal to V over tri 3, since W over L ratio and the current are same. Okay, so that is for the V over tri. And if you look at the transconductance for the first one, if you try the expression for the transconductance for the first one, we can write as I naught is equal to GM1 times the input voltage Vi. Okay, that's the current on the first one. And we can also write this one as I naught over Vi, that is equal to GM1. Okay, so this is also another expression, and we can also give a new name for it, like capital GM is equal to GM1. Okay, so this is for the first circuit for figure A. And if we do this for the figure C, so in order to do it for the figure C, it's better to have a diagram. Like you can also have an equivalent model of this circuit. Here we have two NMOS transistor connected, cascoded. So we can write the draw the equivalent model. If we draw the equivalent pi model, hybrid pi model, this is going to look like this. We're going to have current here, and then output resistance right here, and this one connected to a voltage, and let's call some Vx, and connected to the ground. And this is, so you have to see GDS, ground, drain, and source. Source is in the bottom, ground is right here, and this. Okay, and this is the first one. Plus minus, okay, let's see. Yeah, okay, so we can call one of them as GM VGS2 let's call this one VGS2 right here. If the voltage between gate and source is VGS2, then the current flow through this one is GM2 VGS2, and the output resistance right here is RO2, and here we have I naught current flowing through this, and here we will have negative I naught, and if this is VGS2, this naught right here is negative VGS2, and this one is RO1, and this is VGS1. Okay, plus minus, and the input voltage is also right here, so we can put Vi over here, and Vi and VGS1 are parallel, so we can also say VGS1 is equal to Vi. If you have parallel voltages, all of them are same. So VGS1 here, this Vi, and we can either say GM VGS1 or GM Vi. Both of them works right, and this one is connected to the ground. And the voltage right here, we can say Vx. Okay, and if this is the voltage here is negative VGS2, it's gonna be exact same voltage right here, negative VGS2 as well. So that's one thing you have to know. And other than that, this is the circuit we have, and for this one we can say I naught is equal to GM2 VGS2 as well. GM2 VGS2, and input voltage Vi is equal to VGS1 because these two are in parallel. Okay, so if we apply KCL at the node 1, the node 1 is right here. Let's see what happens. So we had to consider both of the circuits. We had to consider this GM2 VGS2, we had to consider this GM1 VGS1. We can also say GM1 Vi as well. And one is going to the node, one is going out of the node. So you had to take either one of them positive or negative. Like if you take going in as negative, then going out should be positive, something like that. Just keep up with the signs. So if I take the going in as negative, then this is going to be negative GM2 VGS2. VGS2, then here we have negative VGS2, that one divided by the resistance RO2, plus negative VGS2 divided by RO1 also here. And then the current going out of this one is GM1 VGS1, or you can say GM1 Vi as well. Okay, so if we write this one, like here we can take the like terms. So here if I take VGS2 common, and let's say I'm bringing all this term to the other side of the equation, so these terms will become a plus if you take these three terms to the other side. Okay, so let's consider I'm taking all these three to the other side of the equation. If we do that, then this is and also if I take the VGS2 common, this is gonna be GM inside, and then plus 1 over RO2 plus 1 over RO1, and if I this one remains the same in this side, so equal to GM1 Vi, and here this GM is much larger compared to this 1 over RO2 and 1 over RO1, therefore we can say this is just VGS2, this is GM2 right here, so VGS2 GM2, or we can say GM2 VGS2. GM2 VGS2 is equal to GM1 Vi, and GM1 Vi is nothing but is I naught. This is equal to I naught. Okay. and GM2 which is 2 also I naught. Okay, so I can either replace I naught with this one or this one. Both of them are I naught. So let's put I naught for this. I naught is equal to GM1 VI. Therefore, GM1 is equal to VI divided by I naught divided by VI. Which is equal to capital GM. So the transconductance are also equal for both of them. Okay, that's the thing we are proving right here. So transconductance are equal, V over drive are equal. Now let's look at the gain. That's the last thing. So the equation for the gain of a cascoded transistor like this is square. Like if you have AV naught, then if two of them are cascoded, then this is going to be negative A naught square. And for the gain, we derive the equation right here in the part A of the question. That is 2 VA prime L over V over tri. So negative times 2 VA prime L over V over tri whole square. Okay, so this is for the cascoded one. And if you compare the gain of this one and for the first one, if you say AV naught over A naught 1 for the first one, AV naught is this one which found out right here, that's negative 2 VA prime L over V over tri whole square. And for the first one, it is just whatever inside of that is 2 VA prime L over V over tri. This is again for the first one. So from this one you can see we can cancel this one and this square. We cancel this whole term and the square. So this is like we are having negative 2 VA prime L over V over tri left, which is nothing but instead of this whole term you can replace A naught as well. So this is negative A naught 1. You can also say A naught 1 because that is the exact same thing we have. So A naught 1, therefore we can say AV naught is negative A naught 1 times A naught 1. Okay, that's the relationship. It is just squared. That's the thing. That's what they're asking us to prove. Compare these values of those cascode circuit in this one and operating same bias current and same minimum voltage requirement at the drain increase. Okay, so only thing is it is increased by power. And that is it. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.